No, Albert's back on the job. He's holding the page for us. I'm going to start at 7.2. I don't really think there's anything in back in 7.1 that you need me to go through. One thing I want to point out, just like in electric fields where the field lines showed the direction that a positive charge would move, in magnetic fields, the field lines show the direction that a little north pole would move. So if we were to plop a little north pole in here, it would move towards the south. Again, the closeness of the field lines indicates the strength of the field. Right, so in the solenoid video, the video that mentions solenoids, it talks about how the field lines are concentrated in the center of the solenoid. They're close together. All right, hold that, Albert. Thank you. Rightio. So magnetic field around a current carrying wire. Now, magnetism and electricity are really intimately related. They are intimately involved with each other. And wherever you have one, you have the other. So if you put a current through a wire like they've got down here at the bottom of the page, when you put the current through the wire, a magnetic field turns up around the wire and it forms a circle around the wire. They've put compasses there because that's the same as putting a little north pole there, so it shows you which way the field goes. Right? So this is the rule for which way will the field go. You've got your wire that's got a current. This one has got the current coming straight up and through the lid. I put my right hand around it and my fingers will curl around in the direction of the magnetic field. So the magnetic field lines are going around in this direction and the current is the direction of your thumb. All right, so hold it, fingers curl around in the direction of the field, thumb shows you the direction of the current. And they use the same conventions as we were using before. Out of the page, into the page, around the page. That's all. Hop out of the way, Albert. So there's a question down the bottom there. Which direction is it going? Magnetic field at point P is 5 centimeters above the wire, carrying a current of 20 amps to the left. So here we are, 20 amps to the left, so the current's going this way. And the direction of the field up here at P, it's going to be, I can't do it. I was hoping to be able to hold the pen, but I can't. Directly above it, the field is at right angles. So it's like a tangent to the circle. So directly above, let's do it this way. Whoop. Directly above the wire, if that was a circle going around in the direction of my fingers, directly above, I'm going to put an X on my finger. Wait, hold your breath. Are you still waiting? That's because I decided to put an arrow as well. I should get a tattoo. Haha. Righto. Here we go. Sorry. There we go. Whoa. How wrinkly my hand is. Righto. The wire now, we're on the left hand end. We're looking down the wire. And point P is marked there with a dot. And the tangent to the circle right there, the direction of the magnetic field is straight towards my knuckle. So if we turn it now, that magnetic field, right, would be going, and turn it and we'll put it in the same way that it is here on the book, that magnetic field is going straight into the page. So it's a simple formula then. Magnetic field, mu naught is a constant, it's not hard. Current in the wire 2 pi r, and you're done. Right, but you maybe ask the direction of the magnetic field, and it would be into the page. Direction into the page. Hope that makes sense. I know, let's look at this one. These are ones that we've done in class already. I'm just running back over them because with the extra hand signals to try and help you with that. 2 separate parallel wires are in close proximity. Calculate the value of the magnetic field. So the 2 wires will each be generating their own magnetic field. So what you do is you calculate the field at X caused by one wire, and then you calculate the field at X caused by the other wire, and you add them together as vectors. So if they're going in the same direction, then you're just going to add them. But if one's going into the page and one's coming out of the page, then you're not going to be adding them, you're going to be subtracting them. Right, so the working's all here, and we did this one in class too, I think. So the magnetic field at X due to wire A, that's the top one. So if I twist my hand around, right, no, I'm going to have to do it this way. The field is, the current is going to the right, so here we are. And you can draw the little thing on your hand and it might make more sense. It's coming up and around. What would it be doing at X? And if I could contort my hand enough, we would find that at X it's going into the page. Is that what they said? Into the page. That's good. I'm glad Richard and I agree. If you do the same thing for B, a little bit easier for B. All right, there it is. It's coming up out of the page. So that means I'll be doing a vector sum of those 2. Whichever one's the biggest is going to win. And you have to remember, choose a positive direction or just take them away and remember which one was the bigger one. So out of the page. So vector addition, and you end up with 3.2 by 10 to the negative 6 out of the page. I think I'll start a separate video for this because we're already at 7 minutes and it will take a while to do the next one.